Right. So a straight current carrying wire carrying a current I at a perpendicular distance x from itself produces a magnetic field given by mu naught I divided by 4 pi x. Is that what we derived yesterday or not? Yes. Mu naught I divided by 4 pi x cos theta 1 plus cos theta 2. It's very important to understand how to take theta 1, theta 2 in any situation. X is the perpendicular distance, that will be obvious, multiplied with cos theta 1 plus cos theta 2. Now, if you remember, when deriving the result, we took theta 1, theta 2 as the inside angles. When you join the point where you want the magnetic field to the ends of the wire, the angles inside this triangle, you see a triangle forming, the angles inside the triangle were called theta 1 and theta 2 at the ends of the wire. Okay. You can express this result in terms of these angles as well. You can call this as alpha 1 and call this angle as alpha 2. In many books, you find the formula in terms of these angles. How are alphas related to thetas? You can clearly see that there are right angle triangles here. So alpha 2 is nothing but 90 minus theta 2 and alpha 1 is 90 minus theta 1. So you can express the same result as mu naught I divided by 4 pi x cos theta 1 can be written as cos 90 minus alpha 1, which becomes sin alpha 1. And cos theta 2 is cos 90 minus alpha 2, which becomes sin alpha 2. So the same magnetic field produced by a straight wire at a distance x from itself can be expressed in terms of angles subtended at that point itself. Okay. Let's discuss some applications of this. Let us extend this to an infinite wire first. Now you all tell me, I think it's quite easy. If we consider an infinite wire and imagine joining this point to that end which is at infinity, how much will theta 1 become? If the wire is infinitely long, how much will theta 1 become?
0, sir.
0, correct. Theta 2 also will tend to 0. If theta 1, theta 2 tend to zeros, then cos theta 1 will become 1 and cos theta 2 also will become 1. Then that bracket will become 2. You can also imagine in terms of alpha 1 and alpha 2. As the upper end of the wire goes to infinity, alpha 2 will tend to 90 degrees. As the lower end of the wire goes to infinity, alpha 1 will tend to 90 degrees. Then sin alpha 1 will become 1, sin alpha 2 also will become 1. Then you can say that the magnetic field produced by an infinitely long straight wire at a distance x from itself is mu naught I by 4 pi x multiplied with 2 becomes 2 pi x. Okay. This result is also very frequently used in problems. Field due to an infinite straight wire. Okay. And direction, you just have to use the right hand thumb rule. There is another way also to find out the direction. I mean, how we are using the right hand thumb rule is we are finding out the direction of ideal cross R by placing our right hand fingers along ideal and curling them in the direction of R. It will work. Okay. Like in this case itself, if you see, current is flowing upward, point is on the right side. So place your right hand fingers this way and then curl them this way. You will see that the thumb will be pointing into the screen. So at this point, the magnetic field is produced into the screen. That's fine. There is another way also to visualize magnetic field produced by a straight wire. Okay. Now, in that wire, the direction of flow of current must be given to you. Let's say the current is flowing this way. Then the other way of finding magnetic field, let's say you want to find the direction of magnetic field at this point on the right side of the wire. Then what you can do is just place your right hand thumb along the flow of current. Okay. And extend your fingers towards the direction of that point where you want the magnetic field. Fine. And then curl them. You will actually be curling them into the screen. So that way you can tell that the magnetic field here is into the screen. Place your right hand fingers along the flow of current and wait, not right hand fingers. Place your right hand thumb along the flow of current and make your fingers point or direct your fingers towards the point where you want the direction of magnetic field. Then you curl them inwards. Just a moment, I'll search a better image for this. Right. It's like this. So place your right hand thumb along the flow of current and then curl your fingers. The curling of your fingers, the way you curl your fingers, shows you the direction of magnetic field around the wire. Right. So in this second case, if you see, current is flowing upwards and imagine the person curling the fingers. Then on the left side of the wire, magnetic field is out of the screen. And on the right side of the wire, magnetic field is into the screen. And you can even visualize a magnetic field line like this way. And as I was telling you yesterday, magnetic field lines always form closed loops. There are no exceptions to that. Okay. And that is the pattern that they have drawn here also. Right. It's very important to understand how to get the direction of magnetic field because many times you'll be given multiple wires and you'll be asked what is the net field and all. Okay. Fine. So magnetic field produced by a straight infinite wire will be mu naught I by 2 pi x. Finite wire, it will be mu naught I by 4 pi x cos theta 1 plus cos theta 2. Okay. Consider a semi-infinite wire. Semi-infinite means we are able to see one end of the wire, but the other end is at infinity. So consider a wire like this. Assume it carries a current I in the upward direction. Uh, let's say there is a point here at a distance x, at a perpendicular distance x from one end of the wire. Okay. How much magnetic field does this wire produce at this point? Basic formula for magnetic field produced by a straight wire at a distance x from itself is mu naught I by 4 pi x cos theta 1 plus cos theta 2. You just have to visualize theta 1 and theta 2 and based on that, tell how much magnetic field will be produced at that distance x.
So mu naught I by 4 pi x.
It will be mu naught I by 4 pi x, correct. One angle theta 1 is clearly 90 degrees. The other angle theta 2, which will be subtended at the other end of the wire, will tend to 0. So this becomes 1 or okay, theta 1 90 degrees, this becomes 0. Theta 2 is 0, so this becomes 1. Then the answer for magnetic field or the magnitude of magnetic field becomes mu naught I by 4 pi x. So that's the magnetic field created by a semi-infinite wire at a distance x, perpendicular distance x from its visible end. Fine. Another case. Again, consider a semi-infinite wire itself. This time, let's say the point is at a perpendicular distance x, making an angle. Uh, okay, let's take 53 degrees at one end. The other end is at infinity. Then, okay, it's quite obvious. I think you don't have to do any calculation also. The magnetic field here will be mu naught I by 4 pi x cos one angle is 53 degrees, the other angle is 0. Cos 53 degrees 3 by 5, cos 0 is 1. Substitute them, you will get the magnetic field at that position. Now try this question. Let's consider a finite wire itself. The point in this case, okay, the point where we want the magnetic field is like this. The distance is x only. The current is I. Current is flowing upward. And when you connect the point to the ends of the wire, this angle is found to be 53 degrees. This angle is found to be 37 degrees. Current is flowing in the upward direction. Derive the magnetic field at this position. Try this, both of you. I'll give you 2 minutes. Okay. See, the basic formula is mu naught I by 4 pi x cos theta 1 plus cos theta 2. You only need to be careful about theta 1 and theta 2 here. The angles indicated are not always theta 1, theta 2. You need to remember that in the derivation, the angles we had taken were this and this. Okay. So in this case, theta 1 should be taken 180 minus 53 degrees. Then cos theta 1, 180 minus 53 means minus cos 53, that is minus 3 by 5. And cos theta 2, cos 37 degrees, that is 4 by 5, effectively becoming 1 by 5. So the answer is mu naught I by 20 pi x. Correct. Fine. So why is some field getting subtracted here? Why is there a minus sign? Because this part of the wire is missing. This part. Fine. Next, let's say there's an equilateral triangle in which a current flows. Assume the current is flowing this way. Let's say the side of the triangle is A. Calculate the net magnetic field at the centroid of the triangle. By X, you mean A, side of the triangle. Or what exactly is X in your calculation?
Sir, side of the triangle అంటే ఏమి?
Okay, you are given the side of the triangle is A. Answer is expected in terms of A. Fine. See, equilateral triangle, there are three wires, obviously, three finite wires. We'll find out the magnetic field produced by one wire at the centroid, and the other two also will produce the same magnetic field because the current is the same, the angles will be the same, and the perpendicular distance also will be the same. And if the three magnetic fields are in the same direction, we can directly add them. But to calculate that magnetic field, we need this distance first, x. But you're not given that distance, you are given the side of the triangle. Can one of you tell me how to express x in terms of a? How much is the distance from one side to the centroid? This is very frequently used. Side to centroid is 1/3 of the median length. Median total length will be a root 3 by 2. So this becomes a by 2 root 3. That is x in our case. And because it's an equilateral triangle, the angle subtended at the ends of the wire will be 30 degrees and 30 degrees. That's all. So field produced by one wire is mu naught I by 4 pi. In place of x, you write a by 2 root 3. Then cos 30 degrees plus cos 30 degrees. That's all. This root 3 will go to, okay, wait, root 3 by 2, root 3 by 2 becomes root 3. And the denominator root 3 will go to the numerator, it becomes 3. So 3 mu naught I divided by 2 pi A. That is the magnetic field produced by one of them. That's all. Then the net magnetic field, if you consider, see, field produced by each wire. Now the wire that we have considered to calculate the magnetic field, its current is this way, and the position where we are finding out the magnetic field is this way. So ideal cross R, the field will be pointing outwards. Okay. Or imagine placing your thumb along that current, right hand thumb along that current. Your fingers will be pointing outwards if you curl them around that wire. Okay. At the point which we have marked at the centroid of the triangle, your fingers will be pointing out of the screen. So the magnetic field here is out of the screen. Other two wires also, ideal cross R, ideal cross R, they all produce magnetic field in the same direction out of the screen. So the net magnetic field will be 3 times of this. So 9 mu naught I by 2 pi A. Okay. Any confusion in this? Just go through this once, ask if you have any doubt. Next, consider a square frame along with some current is flowing. Calculate the magnetic field produced at its center if the side of the square is given as A. And try to visualize the direction also always. Yeah, we can find this out directly. How much is this perpendicular distance of the point from the wire? Pound
A by 2,
A by 2. And how much will be the angles subtended at the ends of the wire?
45.
45 degrees and 45 degrees. So the field produced by one of the wires will be mu naught I by 4 pi. In place of x, you write A by 2. Cos 45 plus cos 45. 1 by root 2 plus 1 by root 2 becomes root 2. That's all. So this will be, wait, 1, 2 will get cancelled. That 2 and root 2 will get cancelled. Mu naught I divided by root 2 pi A. That's the magnetic field produced by one wire. All four will produce the same field. They will also produce the field in the same direction. Therefore, the net magnetic field at the center of the square frame will be 4 times of this. 4 by root 2 becomes 2 root 2 mu naught I by pi A. Okay. Now from Biot-Savart's law, dB is equal to mu naught I by 4 pi dl cross r divided by r cube. We can say that the magnetic field will be 0 whenever this cross product is 0. Now, one of you tell me, when is the cross product of two vectors 0? The vectors themselves are non-zero vectors, but when will the cross product be 0?
When they are perpendicular to each other.
No. What is the formula for A
Yes.
cross B?
A bar AB sin theta.
AB sin theta. When is sin theta 0?
Sorry, 0 degrees.
When they are
Parallel.
parallel or exactly anti-parallel. That means a current element, you consider a wire like this. Uh, a small part of the wire is what we call as a current element. Consider this current element IDL. It can never produce a magnetic field along this line, the line on which it lies. It cannot produce a magnetic field. Okay, only away from that line, it will be able to produce magnetic fields. Okay, so no current element can produce magnetic field along the line on which it lies. And if an entire wire lies on that line, the wire cannot produce a magnetic field. At points outside that line only, or at points away from that line only, it will be able to produce a magnetic field. Fine. So today we just practiced, so far today we only practiced magnetic fields produced by straight wires. Let us now consider a combination. Fine. Straight wire itself, there's one more case that we need to solve. Okay. Let's say there is an infinitely long wire bent at right angles at one point. So the ends are at infinity. You need to calculate the magnetic field at a point here. Okay, let me make it more mathematical. Assume this is the x-axis and assume this is the y-axis. So it's an infinitely long wire. It is bent at a right angle exactly at the origin. Right. Calculate the magnetic field produced. Okay, I have to give you the direction of current also. Assume current is flowing this way. Calculate the magnetic field at fine, this point 3 comma 4, or let's make it 3a comma 4a. Okay, try this both of you. I'll give you 1 minute. If you have an answer, just unmute and tell. Let's see. The point 3a comma 4a could be somewhere here. Okay. X coordinate is 3a. Y coordinate 4a. Okay. So indirectly, and not even indirectly, directly you are given the perpendicular distances from the wires. What else do you need to know? You need to know the angle subtended at the ends of the wires. One angle is obviously 0 at the end, which is at infinity. The other angle from this point, if you see 3, 4, you can, okay, since that is 3a and this is 4a, tan of this angle is 3 by 4, then this angle is 37 degrees. See, even if you didn't know the exact angle, ultimately what we need is cos of that angle. Cos is adjacent divided by hypotenuse. So here I gave 3 and 4. Then you can tell that this distance to the point will be 5a from the origin. Okay, then cos of this angle 4 by 5. So you don't have to bother about the 37 degrees. It's the cos value that we need. Even if you are given some random coordinates like 1 comma 2. So you take this as 1, you take this as 2, then this becomes root 5. You can tell how much is cos theta. Okay, you don't need to know theta. So any point in this plane, you can find out the magnetic field. So here it's given slightly conveniently. So with one angle, it will be with one wire, it will be 37 degrees. The other wire will be 53 degrees. At the other ends, the angles are 0 and 0. Then field produced by the first wire, let's say the wire which is along the y-axis, it will be mu naught I by 4 pi. The distance from that wire is 3a multiplied with cos theta 1. One angle is 0, so cos 0 is 1, plus cos 37 degrees, 4 by 5. So this becomes 9 by 5. 9 by 3 is 3. 5 gets multiplied in the denominator. So 3 mu naught I by 20 pi A. That's the field produced by one of these wires. 9 by 3, 3 and 5 forces 20. Okay. That is the field produced by the wire which is in the y direction, which is along the y-axis. Okay. In that wire, the current is flowing downwards. So can one of you tell me the direction of magnetic field produced by the wire which is along the y-axis? That wire in which current is going down, in which direction does it produce the magnetic field at that point?
So towards right.
Towards right means like this. Why will the current and the magnetic field be in the same plane?
సార్ నేను చెప్పేది ఎక్స్ యాక్సిస్ లో.
No, even the wire which is along x-axis or whatever, magnetic field will not be in this plane at all. See, there are two ways. You can use the right hand thumb rule. Current is flowing downwards and the point is on this side. Okay. Curl your right hand fingers like this now. Okay, this is what sense, anti-clockwise sense. Curl your right hand fingers anti-clockwise, thumb will point out of the screen. So the field produced by that wire which is in the y direction at this point is out of the screen. Okay. Even if you visualize placing your right hand thumb along the current, then the situation will be like this. Imagine placing your right hand thumb along the current. Then, okay, fingers, thumb should be downwards and fingers should be towards that side. It's difficult to visualize actually. Anyway, it will be like this. And then you curl them. I mean, here, thumb is fine, but for the other fingers, the nails are on the back side. Okay, so if you curl your fingers, the fingers will turn out of the screen. Okay, anyway, for for me, using ideal cross R is easiest. Ideal is this way, R is this way. Curl your right hand fingers in this sense, thumb will point out of the screen. Pawan, is this clear?
సార్ లేదు సార్ అర్థం కాదు.
How are you finding out the direction of magnetic field?
సార్ మీరు చెప్పినట్టే చేసింది సార్. అంటే ఐ థంబ్ ఫింగర్ డౌన్ కిందకు ఉంటుంది సార్.
Thumb will be downwards. Okay.
దాని తర్వాత 3 వైపే ఫింగర్స్ నేను తిప్పాను. అప్పుడు డౌన్ థంబ్ కిందకి వస్తుంది సార్.
మళ్ళీ చెప్పు. థంబ్ కిందికి ఉంది. తర్వాత ఏం చేసినావు?
ఫింగర్స్ ని 3 వైపే తిప్పాను సార్.
థంబ్ కిందికి పెట్టి ఫింగర్స్ 3A వైపు తిప్పితే నీకు యాక్చువల్గా కొంచెం కష్టం అవుతుంది. ద పామ్ విల్ బీ ఫేసింగ్ యూ. ఇట్లా తిప్పాల్సి వస్తుంది కదా. ఆర్ యూ యూజింగ్ రైట్ హ్యాండ్ ఆర్ లెఫ్ట్ హ్యాండ్?
సార్ లెఫ్ట్ హ్యాండ్ సార్. ఓకే.
లెఫ్ట్ హ్యాండ్ యూజ్ చేస్తే ఆపోజిట్ డైరెక్షన్ వస్తుంది. యూ షుడ్ యూజ్ రైట్ హ్యాండ్. ఓకే, ఆర్ యూ క్యాన్ యూజ్ లెఫ్ట్ హ్యాండ్ ఆల్సో, బట్ ద ఆన్సర్ విల్ బి ఆపోజిట్. ఎనీవే ఏం చేసినా కూడా సి రైట్ సైడ్కి అయితే రాదు కదా. ఇప్పుడు లెఫ్ట్ హ్యాండ్ పెట్టినా కూడా thumb will point along the direction of current. Fingers will be towards the point where you want the field. ఇది పొజిషన్ వెక్టర్. మ్యాగ్నెటిక్ ఫీల్డ్ కావాలంటే వాటిని ఇట్లా కర్ల్ చేయాల్సి ఉంటుంది. కర్ల్ చేసినప్పుడు ఫింగర్స్ ఇటు బయటకు వస్తాయి. ఓకే, లెఫ్ట్ హ్యాండ్ అయితే లోపలికి వెళ్తాయి, రైట్ హ్యాండ్ అయితే బయటకు వస్తాయి. ఓకే, దట్ ఆఫ్టర్ కర్లింగ్ వాట్ ఎవర్ ఇస్ ద డైరెక్షన్ ఆఫ్ యువర్ ఫింగర్స్, దట్ ఈస్ ద డైరెక్షన్ ఆఫ్ మ్యాగ్నెటిక్ ఫీల్డ్. గాట్ ఇట్?
ఎస్ సార్.
Okay. So the field produced by this current, which is in the y direction downwards, at that point is out of the screen. Let's call it as B1 or By. Okay. Next, the other wire which is carrying current along the x-axis, it will produce a magnetic field of mu naught I by 4 pi. The distance from that wire is 4a, and angle at one end is 0, so cos 0, 1. Angle at the other end is 53 degrees, cos 53 degrees, 3 by 5. 1 plus 3 by 5 becomes 8 by 5. Denominator, you have 4 into 4, 16. 8 and 16, 2. And into 5, 10. So this becomes mu naught I by 10 pi a. Or you can write it as 2 mu naught I by 20 pi a. Because the other one had denominator 20. Okay. Now, the current which is in the x direction, in which direction does it produce a magnetic field here? Anyone? The current which is in the x direction, in which direction does it produce the magnetic field? Think about it. Okay, let us make use of this. This is someone's right hand. Now, first case, okay, wait. We have to place thumb in the direction of current. So first case, if the thumb is pointed in the direction of current this way, okay, it's not fully stretched out in this diagram, but imagine it is stretched out. Then the thumb will point downward. Fingers are pointed towards the position where you want the magnetic field. And then if you curl them, in this case, the way the person's hand is held, if the fingers are curled, the fingers will come out of the screen. So the magnetic field is out of the screen. Okay, magnetic field produced by the first wire is out of the screen. Now let's consider this wire in which the current is in the x direction. So thumb towards the direction of current. This thumb has to be stretched out like this actually, so that the fingers and thumb are perpendicular. Okay. In this picture, it's not exactly perpendicular. But anyway, when you stretch your thumb out, the arm, okay, and the thumb will be perpendicular to each other. Arm fingers will be aligned. Thumb will be perpendicular to it. Okay. Arm or hand, whatever you call it. So thumb is in this direction and fingers are towards the point where you want the magnetic field. Now you curl the fingers. Which way will the fingers move? Out of the screen or into the screen?
Out of the screen.
Out of the screen. So that second magnetic field is also out of the screen. Okay. Then both magnetic fields are in the same direction. You add them, you'll get the net field. The answer becomes mu naught I by, therefore B net. One of them is 3 mu naught I by 20 pi a, the other is 2 mu naught I by 20 pi a, both in same direction. When you add them, it becomes 5 mu naught I by 20 pi a. 5 by 20 is 4. So mu naught I by 4 pi a. Out of the screen is positive z direction, k cap. Aishwarya, was this the answer you gave?
No, sir.
Okay. Where did you make the mistake?
Sir, in the last step,
Fine, fine. Okay. Let's consider one more question. Let's solve one more question. One of you quickly tell me, what is the formula for magnetic field produced by an arc at its center? Arc of current at its center.
So mu naught I theta by 4 pi r.
Mu naught I theta by 4 pi r, where r is the radius of the arc. Okay. So again, consider an infinite wire. Let's say there is a current I flowing in it. You can imagine how the current will flow in that arc also. Find out how much magnetic field is created at the center of the arc along with direction. Now this time there is that circular arc, okay, that semicircular arc, and there is a straight wire also. The total magnetic field at that point will be field produced by this part of the wire plus field produced by this part of the wire plus field produced by this part. Think about all of them. Every current will produce a field. Okay. I mean, I'm not saying the field will definitely be produced. Every current will try to produce field. So you have to find out field produced by each part of the wire and add them. Try. Or if you can tell directly, tell directly. How much magnetic field will the straight parts create at that point?
0.
0. Because for the straight parts, the point where you are asked to find out the magnetic field lies on the line along which the current flows. Okay. So those straight parts cannot produce any magnetic field. You can tell this way also. The perpendicular distance of that point from the wire is 0. It lies on the same line as the wire, straight wire. So perpendicular distance becomes 0. Therefore, okay, wait. No, you can't answer in terms of perpendicular distance. Ideal cross R becomes 0. You take any element of this wire and the position vector from there, they'll be in the same direction. So that cross product becomes 0. Therefore, the magnetic field produced by the straight parts, there is 0. Only the circular or the semicircular part will create the magnetic field. Okay. So mu naught I theta, angle at the center of a semicircle, is pi divided by 4 pi multiplied with the radius. Radius must have been given to you. That's all. So mu naught I by 4r. What about the direction?
Sir, into the screen.
Here in this case, the direction will be into the screen. See, for curved wires, the only thing you can do is like curl your right hand fingers along the flow of current. Or you take any one element of that wire, say from here to here. Ideal is this way. Point is at the center, ideal cross R. The sense of rotation is clockwise, thumb will point inwards. So into the screen is the magnetic field. Okay. Let's solve one more problem. Just a moment. Okay. Try this question, both of you. Current is given I, radius of the arc is R, semicircular arc. There are two straight parts also. You have to find out the net magnetic field at the point P. So two of them are semi-infinite wires with the with the point lying on the perpendicular drawn from the visible end. So the wires will produce magnetic fields of mu naught I by 4 pi x, mu naught I by 4 pi x. Those will get added. So 2 times mu naught I by 4 pi r, and straight wires, okay, they will produce magnetic field into the screen. And the semicircle, okay, then it cannot be the third option. No? Why did both of you say third option? Consider one straight wire first, forget the other things. The point is here at a perpendicular distance r. Huh. One end the angle is 0, the other end angle is 90. So it will produce a magnetic field of mu naught I by 4 pi r. Mu naught I by 4 pi x into cos theta 1 plus cos theta 2. It becomes mu naught I by 4 pi r. Direction, if you see, ideal cross R, it is into the screen. The other straight wire also, it will also produce a magnetic field into the screen itself, ideal cross R. So 2 times of this into the screen. And the semicircular part, if you if you visualize ideal cross R, or for curved wires, just curl your right hand fingers along the flow of current. The thumb will tell you the direction of magnetic field at the center. So like current is going down from the left side. So going down from the left side, for me, the thumb will be pointing towards me. If I curl my right hand fingers going down on the left side, thumb will be pointing towards me. That means the magnetic field produced by the semicircular part is towards me, means out of the screen this way. And how much will that be? Mu naught I by, circle is mu naught I by 2r, semicircle will be mu naught I by 4r. And this is out of the screen. So answer will be mu naught I by 4r multiplied with 2 by pi minus 1 into the screen, or 1 minus 2 by pi out of the screen. 1 minus 2 by pi pointed away from the page. Answer is fourth option. So both of you made the same mistake. You assume the fields due to the current, straight currents got cancelled. Okay. No, they don't get cancelled in this case. It is clear that they both produce the field in the same direction. Had the situation been like this, and then again continuing straight from here, then the field due to the straight parts would have gotten cancelled. This straight part, current is this way, point is here, ideal cross R clockwise. This straight part, current is this way, point is this way, ideal cross R anti-clockwise. Their magnetic fields would have gotten cancelled. Okay. See, any material module or any practice book you take, you will find a lot of questions based on this. So now you know how to find out magnetic field produced by a straight wire anywhere around it. You know how to find magnetic field produced by a curved wire at its center. Points away from the center we have not discussed yet. At the center, you know. You will find a lot of questions like this in any book you take. Practice a few of them. We'll continue in tomorrow's class.